Hello everybody. Today we'll start with our next topic, or you can say next unit also, that is the moment distribution method over there. Okay, as the name suggests, that moment distribution method, that is, in this method the moments are distributed from your support to the span and again spans to the support in case of continuous or non-continuous beams over there. Okay, but this method is mostly used in the any analysis or any design of beams also further. Okay, unlike as your slope deflection method, this method is also a displacement method over there. But while distributing the moment over there from support to the span or from span to the support, condition is must that your particular support must be a capable support. That is, suppose if I consider any continuous beam A, B, C, out of which suppose at joint A there is a hinge support, okay, at joint B there is intermediate roller support, and also at joint C there is a fixed support over there. Okay, so I have to distribute the moments from A to B and then from B to C over there. But for this distribution of moments, your condition is what? Your support must be a capable support. Capable support means what? That the support which can resist the amount of bending moment over there, or simply you can say the support which resists the bending moment, that support will be called as your capable support over there. Now under this, which type of supports will be classified over there? Now if you see over here, if you draw, suppose somewhat loading is given on this beam over there, okay, and if I have to draw certain bending moment diagram of this, so obviously I'll say that whatever moment I'm going to get at this joint A, that will remain 0 because this is the end support over there. Okay, so somewhat moment will be coming at your joint B and somewhat moment will be coming at your joint C over there. Suppose moment coming at B is X and moment coming at C is suppose Y over there. That means whatever this support is coming, this is not able to resist the bending moment over there. While if you see support B and C, these are resisting some amount of moment over there. So these two type of supports will be classified as your capable supports over there. So under capable supports, which type of supports are there? That is, the first support will be your fixed support. Okay, the property of fixed support is given, that is, it resists the bending moment over there, because in any fixed support, if you consider, there are three types of reactions, one horizontal, one vertical, and along with that you have one moment over there. So in its actual property, it has a bending moment inside it. So fixed support is always a capable support. Second type of capable support, that will be your intermediate simple support. Intermediate simple support. Now simple support means what? That may be your roller support or that may be your hinge support over there. Roller or hinge. That is, if you see over here you are having end hinge support, this will be your intermediate simple support or roller support over there. So this will be your capable support classification, that is, it will resist some amount of bending moment over there. Also in case of frames over there, whatever rigid joints you consider, those are also a capable supports over there. So rigid joints always resist a bending moment and it will be classified under the capable support over there. Now secondly, the second type of support, that will be your incapable support. Okay, so incapable support will be what now? Which do not resist the bending moment, which cannot resist the bending moment. Such type of supports will be classified as your incapable supports over there. So classification under this, first will be what? Now if you see over here, whatever this support I am seeing, that is giving me amount of bending moment equal to 0, which means it is incapable to resist the bending moment over there. So such type of support will be classified as your incapable support. Under this, your external hinge or roller support. External hinge or roller support is a classification of your incapable support over there. Okay, now we have seen in our slope deflection method, that is, the rotational moments and the translational moments over there. That is rotational moments occurring due to theta and translational moments occurring due to the delta over there. Unlike as your slope deflection method, this method is also called as the displacement method. This method is also called as the displacement method, or one more name is given to this, it is also called as the stiffness method over there. So whenever you see displacement method or stiffness method, so what comes in act? That is your degree of kinematic indeterminacy comes into the act over there. That is, you have to first initial step is what? You have to calculate the value of Tk in every numerical over there firstly. Okay. Now we'll revise that terms over there. First, forces or moments, those are occurring due to rotations over there. Rotations means what? That is nothing but due to theta over there. We have seen for this near end and far end moments over there. That is, near end moment rotation, we have near end moment rotation, we take that equal to 4 ei theta upon L over there. We have seen in the relaxation properties over there. That is, in first unit we have seen the diagrams over there by using process of relaxation, how this value comes over there. You can refer that video again for this. Okay, so near end moment it comes equal to 4 ei theta upon L, and while as your far end moment that comes equal to 2 ei theta upon L. So these two moments, why this occurs? Due to this forces due to the rotations over there. Okay, and second term, that was moments occurring due to the translational displacement over there, due to the translational displacements over there, and that those were equal to plus or minus 6 ei delta upon L square. For plus or minus, we have seen the sign conventions for this. For this, if your translational rotation is clockwise in nature, we consider that as negative, and if it comes in anti-clockwise nature, we consider that as positive over there. So these concepts you have to again consider in your moment distribution method also. Okay, so remember this: far end rotation 2 ei theta upon L, near end rotation is your 4 ei theta upon L, and rotation due to translational displacement, it comes equal to plus or minus 6 ei delta upon L square over there. Okay, now for solving the numericals in your moment distribution method, before that we will see certain terms over there, okay, which are useful for the calculation purpose over there. Okay, so you note down the first term, that is your distribution factor. The first term, that is your distribution factor over there. Now in the name you will see that you have to distribute the moments over there. So whatever moments you are going to distribute from span to the support or support to the span, you have to use certain distribution factor for that moment distribution over there. Okay, so that distribution factor, it is defined as, it is the ratio of, remember, it is the ratio of relative stiffness of a member to the total stiffness of a member meeting at the joint. So distribution factor is what? It is the ratio of relative stiffness of a member, that is of a particular single member, okay, to the total stiffness, of all the members meeting at the joint over there. Okay, so suppose I'll consider one example for this. Suppose this example I'll consider here. This is my first member over there, this is my second member, and this is my third member over there. Okay, I am not considering any support conditions over there, just simply members I am considering, and at this joint, that is this is the union of all these three members over there. That means from this joint these three members are originating over there. Okay, suppose the relative stiffness for the first member is K1, relative stiffness for the second member is K2, and relative stiffness for the third member is K3. So what our distribution factor definition says? Distribution factor for a member, it is equal to relative stiffness of a member to the total stiffness of all the members meeting at a joint. That means if I have to calculate the distribution factor for my first member, that is df1 I have to calculate, so that comes equal to what? Relative stiffness of a member. Of a member means what? That you have to consider the first member over there, because you have calculating distribution factor for the first member, so that comes equal to k1 divided by total stiffness of all the members meeting at the joint. Means you have to consider the total stiffness of all the members meeting at this. So k1 is meeting at this joint over there, so you have to consider all the stiffness over there, so that comes equal to k1 plus k2 plus k3. Same way, if I have to calculate distribution factor for second member, that comes equal to k2 divided by k1 plus k2 plus k3, and similarly if I have to calculate distribution factor for third member, that comes equal to k3 divided by k1 plus k2 plus k3. In simple words, I'll just say that is distribution factor is nothing but k divided by summation of k, where k is what? That is relative stiffness of a member, and summation of k, it is nothing but total stiffness of all the members meeting at the joint over there. So this formula you have to remember over there. So this will be our first term, that will be our distribution factor. Now second term, we will see how we have to calculate these values of k over there. Okay, distribution factor we have got, but from this distribution factor, or we'll need k values for calculating this distribution factor. That is how we will calculate relative stiffness, that we'll see now. So mark down your second term, that is nothing but your relative stiffness. Relative stiffness. Okay, so relative stiffness, simple, it is nothing but it is the ratio of moment of inertia of a member to the length of the member. That is simple, I will say that this will be equal to I by L. Okay, so relative stiffness, it is equal to I by L, but this is the case only in case of non-sway frames and in case of beams over there. For sway frames, this case gets changed over there, relative stiffness value gets changed over there. That we'll see further when we'll start with your sway frame topic. But initially you have to remember that is relative stiffness, it is equal to ratio of moment of inertia to the length over there. Now this I by L value, it varies depending on your support type over there. Support type which one? That means your capable support and incapable support over there. Capable support and incapable support over there. For this, understanding these values, I'll consider some examples over there. So first I will see that first case I'll consider. Suppose your far end is fixed one. Far end is fixed one, or you can say fixed is nothing but a capable support. That means whenever you are distributing moment over there from the near end to the far end, while distributing to the far end, your that far end must be fixed or capable over there. Means if I consider this member AB over there, okay, if A is my near end and B will be your far end, so B I am considering it as a fixed one. So B I'll consider that as fixed one. That means this type of support, it is called as a capable support over there. So remember, when your moment is distributed from one end to the other, and if other end has a capable support, your this relative stiffness value, that comes simply equal to I by L over there. Okay, so for all type of capable supports, these values come equal to I by L over there. Now we'll see second capable support over there. Second capable support we have seen intermediate type of hinge over there. So second case I am considering here for far end simple, but your beam is continuous further, or whatever member you consider, that is continuous further over there. That means I am considering the case like this. Suppose A, this is your joint B and this is your joint C over there. So you are transferring moment from A to B and B to C over there. So for the continuous member, B will be joint over there. So for joint B, I am considering a roller support over there. Suppose, okay, you can consider hinge also over here. So B, this type of support, this will be your intermediate roller support over there. That will be called as your again a capable support. Whenever you are distributing moment from A to B or from C to B also. Okay, so again for this type of condition also here this value will remain same, that is equal to I by L. That means simply you can say for capable support your relative stiffness value is equal to I by L. Okay, then now third case I'll see. In case of incapable support what happens? Okay, so for third case what I'm saying, suppose your far end is again simple, but beam is discontinuous, okay, that means your this joint A and B same I am considering, but your beam is discontinuous, that means C joint will not occur over here. Okay, so B is again simple, that means I'll consider roller or hinge support over there, and for distributing movement from A to B, B is your far support over there. So in that case this type of support that will be called as your incapable support. Okay, so for case of incapable support your relative stiffness value comes equal to 3 by 4 of I by L, 3 by 4 of I by L, or you can say simply 0.75 of I by L. Okay, so two values you have to remember over there. Relative stiffness, that is the value of K. Okay, in case of first, that is if your far support is a capable support, your K value comes equal to I by L. Okay, and if your far support is the incapable one, okay, your this relative stiffness value will come equal to 3 by 4 of I by L over there. Okay, so these two terms you have to remember. These two terms you have to remember very carefully over there. Okay, because these two terms are responsible for calculating the distribution factors that we have seen previously. Okay, if this distribution factor comes wrong over there, here this moment distribution comes wrong over there. So very carefully you have to calculate the distribution factors using this relative stiffness values over there. Okay, so this will be our second term, that is the relative stiffness. Okay, now we will see for the third term, here I'll write that. Okay, so the third term that will be your carryover factor, Now carryover factor is what? This is the factor through which your far end near end moment is transferred to the far end moment over there. That means whatever distribution you are going to do, that distribution is to be done with distribution factor, but carryover factor is what? When you are transferring the moment from the near end to the far end, whenever you are transferring the moment from near end to far end, this is to be transferred by using carryover factor. Simply I am writing it as COF over there. Okay, so whatever this carryover factor value you are going to use, that COF value, it is always equal to positive 1/2 over there. That value, it is always equal to positive 1/2 over there. But case is what? When this will be half, your condition is what? That your far end support must be a capable support. What are this moment you are transferring from near end to the far end over there? What are this far end support? That must be a capable support compulsory. Then and then only your this carryover factor will be equal to 1/2 over there. If your this support, far end support, is an incapable support, okay, then your this carryover factor will remain equal to 0 over there. Why? Because incapable support will not take any type of bending moment over there. Barabar? Okay, so that is, if you consider this far end as incapable one, it will not take any type of moment from near end over there. So that means this carryover factor there comes equal to 0 over there. So in case of incapable support, here this carryover factor will remain 0, and this for capable support, here this carryover factor will remain equal to 1/2 over there. So these two things again you have to remember over there. Okay, so all these concepts are related to each other. Okay, so don't get confused and just try to understand over there. Okay, so this carryover factor for capable support, it is 1/2, and for incapable support it is equal to 0 over there. Okay, then we'll see for next term over there. This will be the last term, that is fourth one. It is equal to carry over moment. carryover moment over there. That means what are this carryover factor we are going to consider, that is from near end to the far end over there. In case of the carryover moment over there, your near end moment is transferred to the far end over there. That means if you check the values of near end moment, we have seen near end moment is how much, that is equal to 4 ei theta upon L. Okay, and the far end moment, it is equal to how much, it is equal to 2 ei theta upon L over there. Okay, so if you see the difference between this, that is near end moment, it is equal to twice of far end moment over there. That means whatever this carryover moment you are going to consider from near end to the far end over there, here this carryover moment value, it comes equal to m by 2. So if you divide this value by 2 over there, that comes equal to 2 ei theta upon L over there. Okay, so this carryover moment, it comes equal to m by 2 over there when you are transferring moment from one end to the other. So how we can say carryover moment? Carryover moment, it is the moment carried over to the far capable end when moment m is applied at the near end over there. Okay, so if your m moment is applied at the near end over there, that is equal to 4 ei theta upon L. Okay, so whatever moment will be applied at the far end, that will be equal to m by 2, that is equal to 2 ei theta upon L over there. Your signs of these both the moments will remain same. They will be either clockwise or they will be either anti-clockwise over there. So these four concepts you have to remember. Carryover moment is not mostly used, but the first three concepts, that is the distribution factor, relative stiffness and carryover factor, these three factors you have to remember very carefully over there for solving numericals over there. So we'll revise them again once. So distribution factor, it is what? It is the ratio of relative stiffness of a member to the total stiffness of all the members meeting at that particular joint. That is df simply will be equal to k divided by summation of k over there. Okay, second factor we have seen, that is your relative stiffness over there. Okay, relative stiffness, it is what? It is the ratio of moment of inertia to the length of the member, whichever you are considering. Okay, simply for relative stiffness, what? If your far end support is a capable support, your relative stiffness value will be equal to I by L, right? And if your far end support is an incapable one, then your relative stiffness value, that is, this is nothing but k value. Okay, so that will be equal to 3 by 4 of I by L. And next is your carryover factor term, that is your whenever you are transferring moment from near end to the far end over there, you have to transfer it with a carryover factor over there. And that carryover factor, if your far end support is a capable, this factor will be equal to 1/2, and if your far end support is a incapable, that carryover factor will be equal to 0 over there. So and carryover moment, that will be equal to simply m by 2. So these four terms you have to remember over there. Okay, for solving any type of numerical using moment distribution method over there. Now whatever numericals we are going to solve in moment distribution method, those are based on the iteration methods over there. So that we'll see directly solving the numericals over there. So in next lecture what we'll do, we will try to solve the numericals on the beams, continuous beams, using moment distribution method over there. So if you have understood this, all these three topics over there or four topics over there, you understand it very carefully by watching the video again and again and just study well. If you are having any doubt, you can comment over there. Okay, thank you so much.